So we'll go to the next section. So from here, we're going to go into the detailed calculations, how to determine the 6 elements. Okay, and that involves quite a bit calculations. And before doing that, and let me show you, give you the certain feelings before we proceed. Here is a story of just show you how passionate I have been enjoying teaching this class. Okay, this is the second version of the teaching kits for showing the orbital elements. The way it is this: you imagine this folder as the equatorial plane. Okay. And say, for example, this direction pointing to I, which means pointing, so Earth basically moving around in the space, but here that is I pointing to the installation of iris. Okay, so that is a direction fixed in space. So there's an I. So respect to that one, then here this one representing is the orientations of the orbits. Okay, orientations of the orbits are set orbits. So, for example, we have orbits like this. We might also have orbits like this. Okay, and this one indicating is the shape of the orbit. So basically, the orbits could be like this. Got it? So for satellite 1, once we launch it, the satellite 1 may be just surrounding Earth in this kind of orientation, just keep going, and the size is determined by this one. Or in the same orbital element, the orbit maybe in this way. You got it? So that's kind of degree of freedom. So in this way, you can see if this is the I-axis, this one determining is the first. This is this one, big omega, capital omega. Okay, so that tells us is the orientation of the orbital plane. Then the lowercase omega is this one. So depends on the perigee pointing to the perigee, maybe here, or maybe here. See, that is the second lowercase omega. And the third one is I-axis. I-axis is this one. So once we have this one, so they have a different inclination, maybe this or maybe this. So that's the 3 the elements for defining the relative the orientation of the orbit to the space, to the coordinate systems. Got it? So that is my second version. Where is the first version? First version is very ugly, very ugly. I didn't want to show it. I don't want to show it. So that is the second one, and this one is much better. And again, say for example, I-axis pointing to there. So we have a different orientations like this, and we can change it. The best one is this one. I have machine shop to do it. So let me demonstrate one. Okay, so I don't know whether you can, probably I do this way would be better, okay, in this way. So how about this? We're using this one as our, the vernal equinox at this moment, okay, pointing to that directions. So the orbits can be, say, let me tilt it in this way first. So that is the inclinations of this is the inclination of the orbits, okay. And this inclination of the orbits, and also this inclination also, say, for example, here I show is about 30 degrees. Inclination is fixed. However, it intersections of this axis to the equatorial plane may be different, right? So right now I'm doing is to change the angle of which one in terms of the symbol here. Right now I'm doing is change the value of which. Anyone can see? So this is the axis to I. So this pointing is this one. So right now I'm changing is what value? Anyone can tell?
Omega.
Omega, capital omega, right? Can you see? Okay, and right now I fix the inclinations, so the inclination is fixed. So where this in those symbols here, which value is fixed? For example, I say the inclination is 30 degrees, which symbol that has a value 30 degrees? Inclination is the normal vectors to the vertical k-axis, right? So which value of the symbol is 30 degrees? Would that be I? Right? So again, this represent is the orbital plane. So once I tilt it, that is the I. Okay? So now, how about the omega? Omega simply is the angle. So you can see right now I fixed these orientations and I fixed the capital omega. I fixed. So this one, omega is the way is this. You can see. So say, for example, let me take this one. Say right now here, this point is our major occupied focus. So this point represent is perigee. So lowercase omega simply is telling the relative orientations of this. So that could be here. So for example, here from this axis, basically this axis is the intersections of the orbital plane to equatorial plane. So from here, right now I'm showing this one, the lowercase omega is about 30 degrees. And to here, the omega is about 90 degrees, right? And to here, that is about 180 degrees. Got it? Can you see it? And to here, that one, if we're going down to this, the lower portions, then this will be more than 180 degrees. Okay, so right now I'm doing is to change the small omega, the value of the small omega. Okay? And right now, again, right now I'm doing is to change the value of I. Can you see it? Good? Good? Is this helpful? $2,500. Don't believe it, right? Including materials, including labors. But right now we have all the know-how, all the design. So to replicate, it won't take that much time. So, but this one, yeah, we kind of try a couple kind of try and errors and buy all the needed tools to make something. So here we have some kind of the bearing things, kind of the many small bits kind of embedded there to make these things kind of moving. So advertisement, if any audience on YouTube would be interested, contact me, cchem4@alaska.edu. Let me write that here. Okay, we have a license built up with our intellectual properties office. So basically, this is a property of the university. It's not me, although I'm the creators, but a lot of people involved in this way. Okay, so I will keep this, and then we keep going, and to see how can we proceed to learn those things. And before we don't have those things, we only have first versions, and a little bit harder for get students to understand the things. Before we get into calculation, but this is the first time I see pretty much everyone seems to have a very good concept about this one. So that'll be easier, okay? So the most challenging is to determine the angles between two relative planes in 3D space. That always be the most challenging one. And so here I spend a little bit more time on this way. So here in these figures we constitute is 1, 2, 3 elements. That is about defining the relative positions of the two the planes. And then two, and so we have 3 defined here. Then we have two more. Two more is define the size and the shape of the orbit, and that has been done in chapter 1, and we actually have exercised quite a bit in chapter 3. So that one I don't worry. So we have already have certain calculation. So 3 plus 2 is 5. Then one more, that is the true anomaly, and again we've been exercising true anomaly quite a bit. So basically here I would say the new things for you to learn is how to determine the 3 angles. Okay, the calculation simply is to take the cosine, okay, and later I will show you the details. Okay, so we put the things aside and a little bit, give me one more minute to introduce those kind of, to me, is a weird things. And here is called the we have certain the auxiliary elements. And for example, here this is from our textbook, and also is from the common exercise in astrodynamics field. They, in addition to omega, and we have additional numbers, so say L0, capital pi, U0, and nu 0. Okay, basically nu 0 is simply the true anomaly. So here, let me define a few axes. Okay, first, and I need to run out in a moment. Let me finish this up. Sorry. So here we have few kind of the additional parameters to look at and to determine 1, 2, 3. Okay, so the 3 are based upon really depends on which reference axis you start to measure. So for example, L0 simply is to measure from here to here. What is that? That is these locations. And that is the first weird definition here. You see this one basically is a projections of this one, the plane onto this. And right now we have object here. And on that projection, you can see, compare, I want to explain to you my feelings. And you can see right now in terms of a definition, L0 simply is measured from this axis to here on the projected plane. That means in terms of 3D, that is the angle measured from here, and if we want to really go to the true angle, that should be go around here, right? If you compare this graph. Apparently, if we want to measure the angle in 3D, that will have a different angle as compared to the angle measurement in the projected plane. That is the feeling of my weird feeling coming from. But again, I don't care, and we just follow the conventions of people. So for this one, I would say we wouldn't put more focus on the kind of the additional parameters because they make no physical sense. And I don't know who started this one, but we just follow, okay? And those things, I wouldn't say they are not so useless, but just still useful. They are useful for certain spatial conditions, and later, once we go to there, I will explain to you why they become useful. Okay, so those are the additional arguments, and here I just kind of the highlight here. Okay, and now I want to define a few axes, and the first one is this. So this again, this one representing is the orbital planes in space, and here due to the size of this device, this is so small. But you should imagine the orbital plane basically is the coplane, a coplane with this one. Okay, so any orbital plane can be anything you just want to play. You can play that one. So right now you can see, and the first one I want to define is this one. This is the center of the Earth. So from the center of the Earth linking to this direction, that is what we call the I-axis. Okay, I-axis, and basically it's called the vernal equinox axis. So that is the very first important axis you need to know. Okay, that's always been the reference to all the measurements. Because that one basically is the I-axis of one inertial systems in the universe. I would say they're almost fixed in space, although they changing very slowly along time. 2,000 years, I think the only change is less than 1 degrees. Okay, if my memory is right. So basically, this is the first one we need to know. The second one is once we have the orbits. So for example, the different orbits have a different orientations like this. Okay. So you can see this is the axis of the how to say that one? We'll look at this one, it will be clear. So this is the orbital plane, and that's kind of highlighted by kind of green hatch lines. And intersections of the orbital plane to the equatorial plane. Equatorial plane is our IZ plane, and we have line. So that representing is this one. Okay, intersection is this line. Okay, you can see basically right now this one is fixed, and the line, basically this line definition is called the line of nodes. Line of nodes basically indicating is the collections of the points, which is the intersection between the equatorial plane and the orbital planes. Okay. So in terms of the graph, and that one, that basically is this axis linking. So for example, if this is the I-axis, then from the pin, here I have a small pins kind of linking. So basically the pin, the line of the pins connecting, so the angle, this line is called the line of the nodes. Okay. And the third axis is called this axis, and this axis is called the perigee directions. Basically, that is our the major axis. So when we're going to calculate those angles, we're going to base it on the relative the angles between the three axes. Then we can do something. Okay, and. In terms of our notations, we simply given I notation I to these directions, and we give a notation n and unit vectors to these directions, and we using the notation e, lowercase e, to pointing to the perigee, pointing to these directions. So I, E, I, N, and E are the three kind of unit vectors corresponding to individual axes. Okay, so with those fundamental things in mind, then we can pretty much, I think next page, we can begin to do a little bit calculations. Again, those slides are available, so pretty much you can just listen, and then here the video will be uploaded, and then later you can download the slides, and pretty much you can take the notes, or you can quickly take. So this page, from this page onward, we're going to talk about how to calculate the orbital elements in details. The first one, this page is to show you how to determine the elements which define the size and shape of the orbits. So, for example, if you would able to measure the positions and velocity, then from there you can calculate the angular momentum. Okay, once you have the angular momentum, then you can determine n. What is n? Look at this carefully. Angular momentum is always a vectors and normal to the directions to the plane of this one. This pointing basically is the h directions. Okay, and to determine n is these directions. So from here you can see you simply take the cross product. The k and h, you take the cross product, is that means is this, you can see n is the directions, n is the axis, and that is intersections between this plane and between this plane, the orbital plane, and the equatorial plane. So basically that is the n is the vectors normal to n is the vector normal to basically from here you can see n is normal to k and n is normal to h. Okay, so that is the features. So basically here we want to determine n, we simply take the cross product and then we can get n. And a good exercise, and once you do here is the note you should take to make sure we always stick with the unit vectors. So once you found the h, why not you normalize h into the unit vectors. So here is the normal vectors, here is the normal vectors. Once you calculate it, that will guarantee n you calculate it with the normal vectors. Because once you involve any the magnitude, and that will kind of screw up a little bit, okay? So we determine the n. So n can be determined by this. So again, if you know, you can know the angular momentums, and then you know the k. K is the 0, 0, 1. That's a coordinate 0, 0, 1. Then you can quickly determine n. And regarding the e-axis, and e-axis is this axis, okay, that's pointing to perigee. And this is the one equation we use in chapter 1. And we simply take this, we have velocity, we already have the angular momentum being calculated here. Then we simply plug in this calculation, this is the whole vectors. So you will get the vectors. And again, to be a good exercise, you normalize whatever you calculated and put into to indicate that the direction pointing to here. So in this way, you have three axes, important axes being determined. This I, that's been given, and then you determine this one, also you determine this one already. Okay. And with the three axes determined, then the follow-up is the orbital elements. So P can be calculated by this, and E can be calculated simply is the magnitude of that vectors. And once you have PE, then you can utilize the tables from chapter 1 to calculate everything else. For example, RP, RA, etc. Okay. Don't worry. Later we will have examples to demonstrate the whole process. Okay. And now from this page onward, we're going to begin to determine the three angles. And again. Plot three angles, I, omega, and omega. Okay, so each page for each angle. The first one, how to determine I. The three angles, right now in this page, from this page onwards, we're going to have the three angles to determine. We're going to determine omega, and I, okay, individually. Basically, the angles is this. We base upon the concept if this is a vector A, if this is a vector B. Okay, and then how to determine this. So what is theta here? So that the three angles basically determined is from this concept. And let me do that one. We know that A dot B dot equal to AB cosine theta. So from this concept here, then we can have the theta equal to a cosine, and A dot B dot divided by AB. Right? So that is a simple trigonometry here. So again, for the three angles, simply we're going to find what is A, what is B, then we simply put into these calculations. And so now we look at this one individually. So for this page, we want to determine I. So I is the angles between two vectors, K and H. So we plug into that kind of formula. So again, in that way, the KH here, and then we divide by its magnitude. That's it. No. No. If you only have done this one, then sometimes it will work, sometimes it won't. So for example, as I told you, once we have the cosine, and so this is theta, this is cosine theta. Okay, and again, this is, I think this is, let me put it into here. So this is 180 degrees here, and this one is 360 degrees. I think your calculators, once we punch our calculators, the calculators will always give us, I think it's this range. Say, if you say arc cosine, and say we take minus 0.5, anyone can give, do you have any calculators? Anyone can punch it quickly for us? What is this number? So basically that 123, right?
No, just 120.
Okay, 120. So that one is here. Okay, so that one is 120. Okay, but it's possible this angle also have the value here, right? What is value? This value is, say this is 120, 120. So this value is 240 degrees or multiple. Okay, so for this case, you can see what is I. Again, right now for this case, the equatorial plane is coplane with the orbit plane, so I equal to 0 for this case. Okay, and for this one, I tilted. Basically, I is above. This is the equatorial plane. So that one is above, so this pointing above, so I is positive. So for this case, you can see here, all this case, and let me do the kind of rotation. This one is all positive I, all positive I. Okay, so if for this case, right now, I become 0, right? So let me do this. So this is pointing to I, so this one, right now, right now I'm pointing, this is positive, and now to this case, right now here, sorry, I is 90 degrees, okay? So I is 90 degrees, and right now to this point, you can see right now the orbital, this one pointing downward, so here we have I is more than 90 degrees, okay? And right now here, for this case, is 180 degrees, okay? So for this case, we have to make sure we have to confine the value I is in this case. Okay, so I think for this case we should be fine, and as long as we don't have range. So under this situation, for I we just define here, because for all the calculators that the value give us is from 0 to 180 degrees, and that covers all the possible values we've been talking about here. So this is fine. So nothing special we're going to be care of. Okay. So again, for inclinations, and again, this one we have the note. So basically, the range is from 0 to 180 degrees. We verify from our punching calculator, also verify from the graph here. And the second one is inclination when I equal to 0 degrees. So that is 0 degrees, and that is this case, right? So that's 0 degrees. What that means? That means the orbital plane right away is on the equatorial plane, or otherwise this case. So either 0 degree or 180, that is the equatorial plane. Okay. So under this case, equatorial plane, do we have the accessing the node of how to say? Maybe later we can continue. We can define one more notation. I forgot. So next time we'll come back to define this node. Okay, this name. Okay, so we'll come up here today. Okay, thank you.